day, everyone. This is Kenneth, and today I'll be talking about orthogonal diagonalizations. We begin this presentation with some preliminaries. That A and B with square matrices, we say that B is orthogonally similar to A if there exists an orthogonal matrix P, such that B is equal to P transpose AP. Note that if B is orthogonally similar to A, then A is also orthogonally similar to B by taking orthogonal matrix Q is equal to P transpose. Hence, we say that A and B are orthogonally similar matrices if either is orthogonally similar to the other. If A is orthogonally similar to some diagonal matrix P, that is P transpose AP is equal to D, then we say that A is orthogonally diagonalizable and that P orthogonally diagonalizes A. Let P be an orthogonal matrix and D be a diagonal matrix such that P transpose AP is equal to D. Multiplying the left side by P and the right side by P transpose, we have P transpose AP P transpose is equal to PD P transpose. Since PP transpose is equal to P transpose P, which is equal to the identity matrix, we get A is equal to PD P transpose. Transposing both sides of the equation, we obtain A transpose is equal to P transpose transpose, B transpose P transpose, which is equal to PD P transpose, implying that A is equal to A transpose, or simply A is symmetric. Now we present some results. Let A be an n by n matrix with real entries. Then the following are equivalent. A is orthogonally diagonalizable. A has an orthonormal set of n eigenvectors, and n is symmetric. Now we will no longer show the proof for this theorem, but the basic idea is that you will recall that when you try to solve for the eigenvalues and eigenvectors of A, we get that this is equal to A S is equal to S capital lambda, or simply A is equal to S capital lambda S inverse. You will recall that capital lambda is the eigenvalue matrix, and then S is the eigenvector matrix. In addition, S is an orthogonal matrix, and capital lambda right here is a diagonal matrix. Next theorem. If A is a symmetric matrix with real entries, then all eigenvalues of A are real if and only if eigenvectors from different eigenspaces are orthogonal. Now, to orthogonalize an n by n symmetric matrix, first thing we do is find a basis for each eigenspace. Next, we apply the Gram-Schmidt process to each of the bases to get an orthonormal basis for each eigenspace. Lastly, we form the matrix P whose columns are the vectors constructed in step 2. This matrix will orthogonally diagonalize A, and the eigenvalues on the diagonal of D, which is equal to P transpose AP, will be in the same order as their corresponding eigenvectors in T. Now, to illustrate this, we consider this example. Suppose we want to find an orthogonal matrix P that diagonalizes A, which is equal to 4, 2, 2, 2, 4, 2, 2, 2, 4. Solving for the eigenvalues of A, we get that the determinant of A minus lambda I is equal to lambda minus 2 squared times lambda minus 8, which is equal to 0. So the eigenvalues of A are 2, 2, and 8. Then we have A minus 2i is equal to matrix of 2s, and A minus 8i is equal to negative 4, 2, 2, 2, negative 4, 2, 2, 2, negative 4. Then we get that U sub 1 is equal to negative 1, 1, 0, and U sub 2 is equal to negative 1, 0, 1. That form a basis for the eigenspace corresponding to lambda equals 2. Applying the Gram-Schmidt process to U sub 1, U sub 2 yields the following orthonormal eigenvectors. V sub 1 is equal to negative 1 over square root of 2, 1 over square root of 2, 0, and V sub 2 is equal to negative 1 over square root of 6, negative 1 over square root of 6, 2 over square root of 6. For lambda equals 8, we have V sub 3 is equal to 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. Thus, using V sub 1, V sub 2, and V sub 3 as column vectors for P, we have P equal to this matrix, which we already know orthogonally diagonalizes A. Indeed, we have P transpose AP equal to 2, 0, 0, 0, 2, 0, 0, 0, 8. You can see that diagonal entries in P transpose AP are simply the eigenvalues of A. Now, for the non-diagonalizable case, if A is an n by n matrix that is not orthogonally diagonalizable, it may still be possible to achieve considerable simplification in the form of P transpose AP by choosing the orthogonal matrix P appropriately. We present two theorems for this. Schur's theorem. Let A be an n by n matrix with real entries and real eigenvalues. Then there exists an orthogonal matrix P such that P transpose AP is a matrix the form right here, where lambda sub 1 to lambda sub n are the eigenvalues of A. We denote the upper triangular matrix above by S, so that the equation will be rewritten as A is equal to PSP transpose, which we call a Schur decomposition of A. Hessenberg's theorem. Let A be an n by n matrix with real entries. Then there exists an orthogonal matrix P such that P transpose AP is a matrix of this form. We denote the matrix above by H, which we say is in upper Hessenberg form, so that the equation will be rewritten as A is equal to PH, P transpose, which we call an upper Hessenberg decomposition of A. That's the end of my presentation. Thank you for listening.